And hopefully, if you go to my website, you'll find the video links, and so you can go and have a look at things if I said something and you don't remember it or you didn't get it written down. And also the notes. Everything that's on this paper is appearing in my course website. So you can go and see it. I've got to change mask. Sorry, I can't teach from this one. I got to get my teaching mask. This is the one that I can. No, just kidding. Come on, guys, laugh at me, damn it. I'm trying to make you laugh, and you're hiding behind your masks, and I know you're smiling at least big, but anyway, it's fine. Okay, that's way better. I can actually talk. All right, so, okay. So I'm going to just quickly make a note that, about what I talked about at the end of the last lecture, and then we'll move into the new material. So the very last thing I talked about at the end of the last lecture was the idea of spanning, okay? If you want your set to be a basis, it has to be linearly independent, and it has to span the vector space. And so, oh yes, okay. So one of the interesting things is that if you have a set of vectors which span the space and are linearly independent, then they form a basis, and this leads us to the following result, which is a theorem, which of course means it can be proved. Oh geez. I don't know why I don't just take all the heads off my markers and leave them like that. That's stupid. Anyway, all right, so here we go. Every vector has a unique representation as a linear combination of a fixed basis. Okay? And let's actually very quickly go through this. So suppose there were two vectors in my space, x, which I can write in terms of its components over the basis, and then let's do a separate representation of this. So I could alternatively say this is a sum over the coefficients beta I times xi. So it's the same vector, but this is supposedly two different representations. And all I'm going to prove is that these two representations actually have to be identical. Okay? So first of all, what I can say is if I take it with representation 1, and I subtract what I have from representation 2, what should I get? I should get 0, because they're the same vector. So I should get 0. Okay? So we can, of course, write this out. And using all of the nice linearity properties of scalars with vectors, we get this. But recall that the only way for this set to be linearly independent is when you have a vector written as a linear combination of the basis vectors, and that vector is equal to 0, what must these be? Say it again? Which is? The same as, sorry, I know what you're saying, but what if the vector itself is equal to 0, what must these components of the vector be?
0.
If it's a linearly independent set, these have to be 0, and that of course implies that alpha I is equal to beta I, which means these two representations are the same. Okay? And then I very quickly finished with the idea that to talk about spanning, really and truthfully, if your vector space has a dimension n, and you have n linearly independent vectors, then they obviously span the space. If you have a three-dimensional space and I only give you two linearly independent vectors, they don't span the space. I mean, it's like xy in a three-dimensional space. It doesn't span the space. Okay, so that's pretty straightforward. All right, now, we've got a definition of vectors. And we're going to see that simplify a little later on, but first, we might ask, what can we do to these vectors? And this is where the notion of linear transformations come in. All right. Now, remember, our definition of a vector space has these algebraic properties. Okay, you remember the details of the definition of a vector space? If we want to take a vector space and transform it, we have to be careful not to screw up those algebraic properties. So you can't just take a vector space and do anything you want to it. I mean, you can. I mean, there's no rules about what you can and can't do with vector spaces in the world, but in math, you don't want to screw up the algebraic structure, the parts of the definition of a vector space. You want it to remain a vector space. So we're going to focus on linear transformations. So let me give you a definition of a linear transformation. And again, this is going to be quite abstract. A linear transformation or operator A on a vector space V assigns to every vector x or y on V vectors ax, ay, which also live on V. Okay? Now, if you've messed around with a lot of mappings in math, you might have seen many mappings that take you from one space to a different space. That is not what's happening with linear operators or linear transformations. They are taking you from a vector space back to the same vector space. That's important, okay? All right, but there are conditions that have to be satisfied. For one, for scalars, A and B, we must have A, this is the linear operator, the scalar times a vector x plus B times a vector y. This has to be equal to A times what you get when you act on the vector with a linear transformation plus B times what you get when you act on the vector with the linear transformation. That's super straightforward, nothing weird there. Now, remember in the definition of vectors, we had an addition operation between vectors. That was part of the definition. Do you remember? If you pull out, or you get this abelian subgroup under addition, okay? However, and I hope you remember this, there is nothing in the fundamental definition of vectors that says anything about multiplying vectors. You can add that in, but it's not part of the definition. For linear transformations, there is obviously going to be the ability to add them together, and I might as well write this here. Okay. That might be obvious. However, for linear transformations, there is automatically a definition of multiplication. And the way we do that is as follows. The product of two linear transformations A and B is defined by A, B acting on a vector is A transforming the vector you get by acting on X with B. Does it make sense that this is part of the definition? Because Bx has to be a vector in X upon which A can operate. So using this as our definition of the multiplication of two linear transformations totally makes sense. Okay? All right. This, of course, course, is a definition, so no need to prove it. Now, let's consider some examples. So first and foremost, for Fn, and remember this is the space of n tuples. That is, it's an n-element thing. All right. The matrix multiplication m times a vector v with square n by n matrices works. Okay? So if I'm working in an n-tuple space over the field F, and largely this is either going to be Rn or Cn, real or complex, but nonetheless, if I'm working over an n-tuple space, then matrices, which are n by n, represent linear transformations. Okay? Let's sort of demonstrate that. First and foremost, we know that if I have a matrix acting on a linear combination of vectors, and now I'm going to rely on your familiarity with matrix algebra, okay? A and B are scalars, X and Y are vectors, and M is a matrix. Is this equal to this? Who says yes? Who says hell no? Well, half the class got it right, the other half didn't vote. I don't know what's wrong. But yeah, this is, I mean, just think of it. This is a matrix, this is a vector. These are just scalars. Scalars you can shove anywhere. And you can distribute the matrix, its action, out on a sum of vectors. Okay? Well, that's condition one in finding that this is a linear transformation. So it's satisfied. Okay? Obviously, if we have two matrices, their product is well defined through matrix multiplication. No issue there. Okay? And last but not least, obviously, if we want to add two matrices and have them act on a vector, well, that's the same as letting the matrices separately act on the vector and then adding up the results. Okay? Now, this example you should somewhat be familiar with. That's why I'm giving it first. Now we'll look at a more abstract example. Because remember, there are many, many vector spaces which are not, by definition, n-tuples. So let's consider, go down a bit. Pn. These are polynomials up to degree n. And the operator dk, which is just going to be dk dtk. It's the kth derivative with respect to t, where t is the variable which is defining these as polynomials. Okay? So, consider. Now what I'd like to do is I'd like to demonstrate that this is a linear operator acting on this vector space. Okay? So consider dk on ax plus by. Okay? Well, this is obviously a dkx dtk plus b dky dtk. Okay? You remember what the vectors are? So we can take the basis vectors to be 1, t, t squared, etc., up to tn. That's one basis set. So I'm just taking the derivatives of the basis vectors. So the derivative of this is obviously quite boring, and then da-da-da-da. Depends on the degree of the derivative we're taking. So we could just do k equals 1, all right? But that this holds is basically a reflection of what you understand from calculus. That's all I'm asking for, okay? That's all I'm asking for. Nothing sophisticated here. All right. Oh, wait a minute. Hang on. So x and y are on Pn. Those are elements of this space of polynomials. That's a given. Are these elements of Pn? Yes. Okay. So these are on Pn as well. Okay. But that's what we should expect. All right? Okay. What about the multiplication of these operators? So if I pick two different transformations and act on a vector x, well, this is just dk, dtk, dk prime, dtk prime acting on x, where again, this takes a vector, gives me back a vector, upon which I can act with this linear transformation. But of course, this has the obvious result of the product, that you're taking the k plus k prime derivative. Okay? Notice, for matrices, I'm multiplying matrices. Here, I'm taking higher order derivatives. Not at all the same. But this is the definition of the product in this case. And then lastly, of course, we have the dk plus dk prime acting on x is obviously equal to dkx plus dk prime x. Okay, nothing odd there. Okay, so here's two examples of linear transformations of vector spaces. Now, I have a question. What about the integral of a vector x, where x lives on this polynomial vector space, where the integral would simply be integral x dt? Is that a linear transformation on this vector space?
No.
Why? Exactly. If you put in the highest power of t allowed, say this is a p3, so that you could have things up to t3, well, the integral of t3 is proportional to t to the fourth, which is not part of the vector space. Okay? So again, the linear transformation is not mapping between different spaces. It's taking vectors in a space and mapping them to vectors in the space. Okay? All right. There are two special linear transformations. There is the zero transformation, which acting on any vector gives you back 0. Okay? Is this an element of the vector space? Man, I wish I had my deck of cards already. I'd flip it over. You! Is this an element of the vector space?
I remember this came up and you said the zeros were funny and they're not really, are they not really in the space zeros or are they just?
So in the definition of a vector space, what's the first condition? Everybody go back to the definition of a vector space and tell me what the first of the two conditions are. Is 0, exactly. Every vector space has to have 0. So I can take any vector you want, act on it with this linear transformation, and you get back a vector in the space. It happens to be the most boring, simple vector. It's 0. But that is guaranteed to act in every single vector space. Or sorry, it's an element of every single vector space. 0 is not an element of every set, right? It's not the set, it's not in the set of irrationals. Okay? There's plenty of sets you can throw at me that don't have 0. But every vector space has 0 as one of its elements. So this satisfies that mapping, okay? And then of course you have the identity, which just gives you back x. All I'm saying is that 0 and I are really simple examples of linear transformations. Because clearly the identity takes an element of the vector space and gives you back an element of the vector space. It just happens to be the same element. Okay? All right. Now, the product of two linear transformations enjoys a set of interesting properties. First and foremost, any linear transformation times 0 is the same as the 0 times the linear transformation and is equal to 0. Okay? That's kind of obvious, actually, even if you want to just regress your thinking back to arithmetic, even though this is hardly arithmetic. All right? Similarly, AI is the same as IA, which is the same as A. And then more interestingly, we have, if we have a linear transformation acting on the sum of linear transformations, then the action is actually distributive. We have associativity. We have the behavior of scalars. And one of the things that I want to note in this is that AB equals to BA is not required. Okay? So you can have two linear transformations of a vector space which do not commute with each other. That's fine. Okay? Any questions? Okay. All right. I'll probably regret this, but let's just go on. All right, so now that we have linear transformations, where these are basically taking a vector space and the linear transformation you've given me. So you can give me a single linear transformation, but I must be able to act on every single vector in the vector space with that linear transformation. So you can't say, oh, this linear transformation only acts on this handful bound at the bottom. It doesn't, no. If you're going to give me a linear transformation on a vector space, it has to act on every vector in the vector space, and the result has to be a vector in the vector space. Okay? Now here's an interesting question. Is there an inverse to that? If I've got a linear transformation which is taking vectors into vectors, can I always just create an inverse that carries me back to the vector I started with? Of course, the answer is no. And we're going to explore that, okay? So, and this is actually going to have huge practical implications because you'll use this idea in solving a lot of linear systems. Okay, so first and foremost, does a linear transformation have an inverse? Well, when I use the word inverse, that usually means I take something, I combine it with its inverse, and then I get the identity. But linear transformations enjoy two kinds of ways of combining, right? You can add them, and you can multiply them. So when I ask about inverses, which one am I talking about? What do you think? Well, you could ask it for both of them. It turns out that when you talk about the addition of linear transformations, there's always an inverse. Why? Because linear transformations, actually, I should be a little bit more complete. The set of all linear transformations, so you Take all possible linear transformations.
I've got a helmet in there.
That's fine. Are you going to put it on before you walk out the door? You need to put it on. Oh, it looks good. It's good.
Prepared.
Looks like a watermelon. Nice. Careful. If I take a vector space and I consider all linear transformations on the vector space, what do you think they form? Any guesses? They form a vector space. I know. This is where it gets so weird. You take a vector space, you define these transformations on the vector space. All those transformations form a vector space as well, but they do. Okay? Now the reason that's important is because if they form a vector space, what must they have? What's the first defining quality of a vector space? It's an identity in the addition part, but it's the addition operation. It's a vector plus its inverse equals 0. But what is the additive inverse of a vector? It's just minus 1 times the vector, which is always part of the vector space. Okay? So what I'm saying is the fact that the full set of linear transformations on a vector space forms a vector space itself means that for the addition of two transformations, the addition operation must have an inverse. It's just minus the transformation. Where it gets interesting is when you ask about the inverse of the multiplication part of the story. That's more interesting. Okay? All right. Okay, so I'm going to very quickly do a little notational fix. First of all, we could call this this unknown inverse that we're interested in the multiplication inverse, okay? And then if I multiply them together, I should get I. And then we might call this the additive inverse, okay? But I'm not going to carry that around. That's just too much, okay? Obviously, you know what the additive inverse is. This is always just minus A. So we're just going to skip that and skip that. So whenever I'm referring to the inverse of the linear transformation, I'm talking about the multiplicative, okay? Because the additive is so simple. And that's just the standard. Okay, so, all right, here we go. If a linear transformation, A, has both the following, then A inverse exists. And here are two conditions. If I start out with two vectors which are not equal, okay, then this implies that linearly transforming the first vector and linearly transforming the second vector will also give you vectors which are not equal. Okay? If this is true, then that's at least part of the conditions that have to be satisfied for A to have an inverse. There's another way that we can say this, which is if the linear transformation of vector x equals the linear transformation of vector y, then this means that the vectors are the same. Okay? Those basically both say the same thing. Now that's one condition. There's a second condition. But we'll be interested in the fact that there are two. For every y on the vector space V, there exists an x on V such that ax equals y. Okay? That is, if I consider my array of vectors in the vector space, and I pick one of them, in order for the linear transformation I'm thinking about to have an inverse, I have to be able to write this vector as the transformation of another vector. It might be the same vector, but it's got to be the transformation of a vector. Okay? Now, this is in a sense a definition. No point in trying to stop and prove anything. Okay? Green means go. Now what I'm going to do is start out with an example, and then we're going to dig a little deeper into what do these things mean, and do we need both of them? Because it's going to turn out that at least for finite dimensional vector spaces, we do not need both of them. Okay? So let's start out with some examples. Or let's start out with an example. Maybe I've got, yeah, I'll do two examples. So first, example 1, consider a rotation by an angle theta in the two-dimensional plane. Okay, cosine theta minus sine theta, cosine theta, which I'm just going to imagine that this is acting on R2. That's the two-dimensional plane, so it's acting on an n-tuple, a two-tuple of real values. Okay? Now let's prove that this has an inverse. So if I take a vector x, which has its components a and b, and I take a vector y, which has its components c and d, then we can first and foremost construct the rotation of vector x, which is going to give me a cosine theta minus b sine theta, a sine theta plus b cosine theta. And then I can separately enact the linear transformation on vector y, sorry about that, which is going to give me c cosine theta minus d sine theta, c sine theta plus b cosine theta. Okay? All right. Now, what we're going to do is we're going to use this condition, this version of the first condition. Okay, so I'm checking out quality A, and we'll check quality B in a minute. But instead of using the negative, I'm going to use the positive. So let's set the result of applying the linear transformation to x equal to the result of applying the linear transformation to y. Okay, so I'm just going to put an equal sign here. And let's see if this forces vector x to be equal to vector y. Okay? Well, all I'm doing is I'm taking the first element of this and setting it equal to the first element of this, taking the second element, setting it equal to the second element. This is going to give me two equations, which I can simplify into the following form. A minus c times cosine theta, I'm doing a little bit of moving things around the equal sign, is b minus d sine theta. And the second terms being equal gives me a minus c sine theta equals minus b minus d cosine theta. Okay? Now, for both of these to be true, what can you tell me about the relationship of A and C and B and D? Well, let me ask you, if both of these equations were true, Why don't I just divide this equation by this equation? Is that ever true? Nope. Never. So this can never be true. So in order for this set of equations to be true, what must I require? I need A equal to C and B equal to D. That is, I have to have the vectors be the same. That make sense? Okay. Quality B, for every vector y on B, there exists a vector x on B such that A acting on x gives me y. Well, if I take y to be AB, then there is a vector x, which is A cosine theta plus B sine theta minus A sine theta plus B cosine theta, such that r theta on x equals y. Okay? You can do that. I mean, you can act with the rotation matrix on this and you'll get this. This is obviously an element of the space as well. So B is satisfied. So if A and B are both satisfied, then clearly this linear transformation has an inverse. Can anybody tell me what the inverse is? Hopefully you realize a rotation has an inverse. What's the inverse? You're going to rotate by an angle theta. To do the inverse, you rotate by the angle negative theta. Of course, cosine is symmetric under the exchange of theta with minus theta. Sine is anti-symmetric, so this is just cosine theta, sine theta, minus sine theta, cosine theta. Okay, whoops. Of course, we could have found the inverse in the first place, and that would have proved that there's an inverse. But I wanted to show you the satisfaction of these two conditions, because these hold for all linear transformations that have inverses. Okay? We could always get into the guts of an example and just find the inverse. Okay? In fact, having gone through the guts, we can now apply this to a more abstract example. Any questions on this? All right. Any more abstract example, and I hope you realize I'm just going to beat the crap out of these polynomials. How about D on Pn? That is the first derivative acting on the set of polynomials to degree n. Does this have an inverse? Well, let's consider the two conditions. Condition A, if I take as my vector starting point t squared plus t, where I'm thinking of a polynomial space where n is at least t2 or larger, okay? It doesn't really matter. If this is a vector on the polynomial space, and y is t squared plus 3. Okay? Note, dx equals remember d is the derivative with respect to t. So it's, oh, sorry. Sorry, I miswrote this. That's 2. My bad. You said the right thing, now say the right thing based on what's on the board. 2t. What about dy? It's also 2t. So the linear transformation acting on these two vectors gives me the same result. Are the vectors the same? No. Clearly this is in violation of A. Pick which value you want. Okay, we just showed that these are the same, but these are not. So this being the same does not imply this. That is a reflection of the fact that the inverse does not exist. Okay? Alternatively, we can consider condition B. For y equals 2t to the n plus dot, dot, dot. There exists no x such that the derivative acting on x equals y. That is, if you take the highest element of Pn, so n here is the same as the n here, there's no element of the set which you can act with the derivative on to get this vector. Because the derivative, the action of the linear transformation is to reduce the degree, okay? So both of these conditions are not met. Well, as we pointed out, there's no inverse in this case, okay? All right, now you might have noticed we met both conditions. You might ask, well, is it possible that we violate this one, but we keep this one, or we keep this one, we violate this one? Well, now we're going to prove that, nope, if you violate this one, you must violate this one, and vice versa. Okay? So let's have a look at that, and this is going to sort of require us going a little bit more deeper into what these conditions mean. All right? So, condition A is the condition of what we often call injectivity. That is, it is a one-to-one mapping. And maybe I'll say A instead of 1. Okay. So what do I mean by a one-to-one mapping? Well, let me give you examples of injective and non-injective maps. So injective maps, and then I'll do non-injective maps. So I'm considering maps between elements of spaces. I'm just going to do a few examples. So I'm just going to map from this space to this space to this space, et cetera, et cetera. Okay? All right. So for injective maps, say the space I'm starting with has two elements, and I'm not talking necessarily about vector spaces here and linear transformations. I'm just talking about the more abstract definition of injective and surjective. And then we will consider how these things play out in the case of linear transformations on vector spaces. But what I'm saying now is very generic, okay? So if the space I'm mapping from has two elements, and the space I'm mapping to has two elements, then an injective map is one where this element gets mapped there and this element gets mapped to the other one. That is, it's a one-to-one mapping. Okay? Alternatively, I might have one element in my starting space, and that single element actually might get mapped to two different elements in the target space. That's clearly non-injective. That's not one-to-one. Okay? Now I want to be careful because I could have two in the initial space and maybe three elements in the target space, and it might be that the two in the initial space are mapped to two in the target space, but they don't cover the entire target space. Okay? This is still injective. It's one-to-one. Okay? Yet another example of a non-injective map is where you have two things in your starting point and you map them to the same thing in the target space. Can anybody give me a really simple example of this kind of map on anything you like? No, a concrete example, a specific, like, I mean, you can obviously do it with differential equations. Can you give me a differential equation that does it? Don't even go there, just literally think about it.
Square root.
Square root, exactly. What about this one?
X squared.
Yeah, x squared. Okay, so it is not the case that every single map is one-to-one. You can have plenty of maps in math that are not one-to-one, okay? Now, condition B, that is the condition here, that for every y there exists an x on V such that ax equals y. This is also known as surjectivity. That is, it's onto. The map must be onto. Okay? So once again, we'll look at examples. And by the way, I don't know if you realized it or not, but I'm in the habit now, although it was only like an hour before class because I actually forgot, I'm going to post my notes before lecture. So if it helps to go over them, I won't get them much more than a few hours before lecture, but I will post them. So if you want to print my notes out and bring them in and just mark my notes, that's fine. Okay? Sorry I didn't tell you about that earlier. Okay, so let me draw some pictures of surjective maps. And of course, pictures of non-surjective maps. Okay? So for a surjective map, what we have in mind is first and foremost satisfied by this initial example. That is, the target space has two elements, and both of those elements are being mapped to from elements of the initial space. Okay? Of course, we could have this non-injective map that is surjective. It's obvious this is not injective because it's not one-to-one, but it is surjective. Okay? And then for non-surjective maps, we might have two elements in each, our beginning and our target, but if the two elements in our beginning map to the same element in the target, you're not getting something that maps to every element of the target space. Okay? Similarly, we could have more elements in our target space than we have elements in our initial space, and even though it's a one-to-one mapping, it's not onto. Okay? Well, are you ready? Notice that to have an injective map, which is not surjective, requires this space to have a different number of elements than this space. Okay? To have a surjective map, which is not injective, requires this space to have a different number of elements than this space. Everybody see that? Okay, clearly this map is both injective and surjective. Now, let me ask you, if I have two spaces and they have the same number of elements in each, does injectivity force surjectivity and vice versa? Yes, it does. Everybody see that? Everybody sees it? Good. Now, a linear transformation maps from a vector space to the same vector space. If it is injective, it is also surjective. If it is surjective, it is also injective. It doesn't have to be either one of them. Exactly. So it turns out that for linear transformations of vector spaces, since the things I'm mapping from and to always have the same number of elements, I could just prove the injectivity of the map, and this comes along for the ride. Or I could prove the surjectivity, and this comes along for the ride. Okay? Of course, the whole point of this is to prove that there's an inverse. Okay? The multiplicative inverse of linear transformations. Okay? All right. So now we can put the condition for a linear transformation to have an inverse in even simpler terms. Okay? And we can do that with the following theorem, which we'll prove in a few steps. If AX equals 0 implies that x equals 0, then A inverse exists. Okay? Well, let's show this. Okay? Well, first of all, we can pick either one of these to work with, because now we know if one of them is true, the other one's true. So let's pick the first one. And let's say AX equals AY implies that x equals y. Okay? Well, now let's just rearrange it. So let's do AX minus AY equals 0, because AX is equal to AY. But this is A times X minus Y. But if A is invertible, this means that X minus Y is 0. That is, X is equal to Y. Okay? Okay, it's fine. Are there any questions? Okay. All right. Go ahead and erase this and probably regret it later on, but that's the way it goes. Okay, it turns out that if A inverse exists, if the inverse of a linear transformation exists, obviously it's also a linear transformation, and so A inverse satisfies the linearity conditions. All right. Moreover, if A inverse exists, then these two linear transformations actually always commute. That is, I can go AA inverse or A inverse A. Both of them are going to give me the identity. Okay? To finish up on inverses, if A and B are invertible, then so is their product, AB, with the inverse of the product being B inverse A inverse. Okay? Why do we reverse the order? Any takers? I mean, this is kind of like distributing the -1, but then we reverse the order. Why do we do that?
You did it with A, B, we did the A's to A's and the B's.
Exactly. This is supposed to be, whoops, the inverse of AB, which is the identity, but if we want to break that down, then that's the identity, and then the B inverse B. Okay? So that's the reason we're reversing the order. Okay? If A is invertible and alpha does not equal 0, okay, alpha is just going to be a number, real or complex, then alpha A inverse is 1 over alpha A inverse. That is, numbers just go for that multiplicative inverse ride. Okay? And then 3, which is one of those really obvious ones, if A is invertible, so is A inverse. That is, A inverse inverse equals A. Okay? Now I want you to remember, I am talking about multiplicative inverses, but in general, we are not saying this. Oh, well, you just divide by A, that's the multiplicative inverse. No. This is only true if you're dealing with numbers. If you're dealing with anything more complicated, it doesn't take this form. So for example, matrices. The inverse matrix is not 1 over, the inverse of a matrix is not just 1 over the matrix, okay? So just keep that in mind. Any questions? Okay, so I don't know how far I'll get, but we'll see. All right, now I'm going to take what is going to seem as a detour, but when you see the final product of it, you'll be like, oh yeah, that's what I figured. Geez, now it all makes sense. But I got to get through the detour first. So, let us for a moment consider isomorphisms. Okay? Now, in order to explain isomorphisms, we're going to go back to a simpler structure, and that is the structure of a group. So generically, remember, a group is a set of elements, and then there's a single operation that combines 2 elements from the group, and then that operation has to satisfy a bunch of requirements. It's got to be closed, there's got to exist an identity, there's got to exist inverses, it's got to be associative, all this stuff, okay? But nonetheless, it's a set with 1 operation, okay? Now, if I have 2 groups, and they have the same number of elements, does that mean, in a sense, they are equal? Hell no. Exactly. Defining a group is way more than just saying this is my set. The operation is a huge part of the definition of a group. Okay, so I have to, if I want 2 groups to be equal in some sense, they have to have the same number of elements, but also the operation in combining elements has to have the same sort of algebraic structure. If that is the case, then I can say the 2 groups are isomorphic to one another. They're not equal in the sense that, you know, things just aren't equal. I'll give you some examples in a moment. But they are equivalent in the sense that in terms of squinting your eyes and going, well, there's 4 things there and you can combine them in this way, and those 2 things look exactly alike if I'm squinting my eyes to those features. Okay? So that's what isomorphism is. So let me give you some examples. First of all, if you have a group and you want to display its algebraic properties, the simplest way to do that is through a multiplication table or a Cayley diagram. So for example, here's the simplest group I could imagine. Take the number 1 and the number -1 as your elements and consider the operation of multiplying. This satisfies all of the properties of a group. Okay? We would like to exhibit the structure through a multiplication table. So here's my multiplication table. Well, I've got 2 elements, so there's only 2 things I can do. I can multiply 1 by 1, I can multiply -1 by 1, I can multiply -1 by -1, or I can multiply -1 by 1. Okay? Well, it turns out if I do 1 by 1, I get 1. If I do -1 by -1, I get 1. If I do -1 by 1, and I do 1 by -1, I get -1. Okay? That's it. We just displayed the entire structure of this really simple group. Turns out for groups with finite numbers of elements, you can always do this through a multiplication table. If there are 973,426,683 elements, it might be a little bit big, but you could do it. Thank you for laughing. All right, so what I'm going to do now is I'm going to give you an isomorphic group, a group which is basically the same, even though it's defined in an entirely different way. Consider the set of all even numbers and the set of all odd numbers with addition. Well, if I construct the multiplication table, where the combination of two group elements is actually just addition, then I find two evens add to an even, two odds add to an even, an odd and even adds to an odd, an odd and even adds to an odd. Notice, if you squint your eyes, these two pictures are the same. And then one more quick one. If I take the identity and a rotation in 2 degrees by pi with plus, yet a third. Okay? So it turns out that all of these groups are isomorphic to each other. Again, being isomorphic means they have the same number of elements and their algebraic structure. Whatever operation you're putting on there, that has to be the same as well. Well, just throw this at you because I'm going to put it on your homework. It turns out any group with 2 elements is isomorphic to all of these. You can't have a group with 2 elements which doesn't satisfy this. But anyway, you'll look at that in your homework. At any rate, now, what's important is that if I'm claiming an isomorphism, then it has to go both ways. Because, for example, we can take rotations in 3 dimensions and we can map those to rotations in 2 dimensions, basically by projecting. Okay? So you might say, well, if there's this map from 3-dimensional rotations to 2-dimensional rotations, does that mean they're isomorphic? Well, the map's got to go both ways, and the map does not go this way. Okay? Now, let's go back to vectors. Two vector spaces, U and V, over the same field are isomorphic if there is a 1-to-1 correspondence between, don't write U, between an element of U and an element of Y, and vice versa. So that we can say, if yi is some function of xi such that f alpha 1 x1 plus alpha 2 x2 equals alpha 1 f x1 plus alpha 2 f x2. seems pretty obvious. Okay? But I can take this definition and I can do a proof, which I'm not going to show you the proof. I'm just going to give you the result. Okay? Using this definition, you can prove the following. Every n-dimensional vector space Vn over a field F, every single vector space that has dimension n over a field F is isomorphic to the n-tuples with elements of the fields. Huh. Is that true? Yeah. An immediate consequence of this is that if I give you a vector space of dimension n, and I give you a different vector space of dimension n, since both of those are necessarily isomorphic to Fn, they're also isomorphic to each other. If A is isomorphic to B and B is isomorphic to C, A is isomorphic to C. It's that simple. Okay? Now, I don't know how far I'll get, but I'll give it a try. Vector spaces can be defined in terms of, arrows pointing out R3, that kind of thing. They can also be defined in terms of these polynomials. But any vector space is automatically isomorphic to the n-tuple, where n is the same as the dimension of the vector space. An n-tuple is literally this. This means that any linear transformation on the original vector space is isomorphic to what? A matrix. This is why matrix algebra is so damn important. It turns out that you can be working with something super abstract defined in terms of derivatives, but at the end of the day, you can set that up as a matrix multiplying a column vector. Okay? Let me show you an example. Let's take the operator d, which is of course d by dt, and I am going to consider a vector x, this is just going to be on P1, the simplest example. So I'm going to take the vector alpha naught plus alpha 1t. This is P1. It's the space of polynomials of degree 1 or less. And then what I know is that d acting on the vector x is just alpha 1. Okay? All right, now, if we use the basis 1 and t, then what we can say is the following. dx is a matrix times alpha naught alpha 1, and its action on the vector should give me alpha 1, 0. Okay? Because the first component is whatever's sitting here, it's a constant. The second component is the coefficient of t. Once I take the derivative, I get this coefficient, but it's not sitting in front of a t, so it's moved from here to here. And then, of course, there's nothing here. Does everybody understand why I wrote this? What's D?
0, 1, 0, 0.
Yeah, D is 0, 1, 0, 0. Boom. Okay? Now, suppose that instead of working in the basis 1 and t, I wanted to work in the basis 1 plus t, 1 minus t. There's not a single basis that you have to work with in any vector space. You can use any basis you want. Okay? Well, how are we going to do this? Well, let's first and foremost write the vector x here, because I know how d acts on the vector x here. I'm going to demand the same thing down here, but I have to express the vector in the new basis. Well, if we do that, what we have is x is 1/2 alpha naught plus alpha 1 times 1 plus t plus 1/2 alpha naught minus alpha 1 times 1 minus t. Okay? Just write that down. Trust me, this is the same thing as this. Okay? So this, of course, means that writing x as a column vector is 1/2 alpha naught plus alpha 1 and 1/2 alpha naught minus alpha 1. And then we can actually go ahead and enact the action of dx. This is just going to be 1/2 alpha 1, 1 plus t, plus 1/2 alpha 1, 1 minus t. Okay? Dx is a vector itself. So it's got to have a 1 plus t component and a 1 minus t component. We're just expressing it in terms of this new basis. Okay? But this combination gives me exactly this. Okay? Everybody see that? So now what we're going to demand is that in a matrix form, the matrix form of D acts on the column vector form of X to give me 1/2 alpha 1, 1/2 alpha 1. Therefore, D takes the form 1/2 minus 1/2, 1/2 minus 1/2. Okay? Any questions? All right, so I'm gonna really quickly in 30 seconds, I'm gonna write down some properties. These are just properties of matrices. These are things with which most of you are very familiar, okay? So I'll just get the list down really quickly and then we'll go. And I gotta get this list down because I do have a homework question that I'm gonna pose which uses for part of it. Diagonal matrices always commute. Okay, he's writing some really obvious stuff. Idempotent matrices satisfy A squared equals A. And this includes 0 and I as examples. 0 times 0 is 0, I times I is I. Okay? Given the elements of A, that is Aij, where Ij just labels the row and column. RC circuits, that's the way I remember that. First index is the row, the second index is the column. Then the transpose has elements. This is obvious. That is the elements of the transpose of the matrix. Transpose is indicated by a twiddle. I know you're used to a T, but we're just going to do, or a capital T, but we're going to use a twiddle to keep in line with the book. The ijth element of the transpose of the matrix is just what you get by flipping the indices. Okay? Now what's important is the properties of transposes. That is, if A twiddle equals B, then B twiddle equals A. And A plus B twiddle is A twiddle plus B twiddle. And last but not least, AB twiddle is B twiddle, A twiddle. Okay? These are results you can get from the definition. All right, and I won't even write the rest of this stuff up here because this is so obvious you can just read it in the notes. But you can add complex conjugation, okay? And in that case, your twiddles are going to turn into daggers, Hermitian conjugates. Okay? But everything is going to be the same. All right? And then you can have symmetric and anti-symmetric matrices. So a symmetric matrix is one such that the transpose is equal to the original matrix. And an anti-symmetric is one where A twiddle is equal to minus A. So if you transpose, you get minus. And one of the interesting things is that any matrix can be decomposed in terms of a symmetric plus an anti-symmetric combination. Okay? This is something you should have seen before. Taking an arbitrary matrix and reducing it to a sum of a symmetric and an anti-symmetric. Okay, so, sorry, it took me more than 30 seconds. In the notes, I give you some indication here, all right, of how these matrices are being notated in the book, okay? So have a look over this. If you have any questions on this, just ask me in class on Tuesday. I'm not giving you a homework problem over this, so you're fine, okay? See you guys next Tuesday. If you got anything you want to ask me about, just come up. I'm fine with chatting with you, and I will post my office hours tomorrow.
What's the difference between indifferent matrix and the projection operator?
Sorry, say it again?
What's the difference between indifferent matrix and projection operator?
What's interesting is that a projection operator is an indifferent matrix,
Yeah, but it's more general.
but indifference is more general.
What's the other, what else the projection matrix?
Sorry, say it again?
What else the projection matrix have to satisfy? A squared equals A. I don't know.
Yeah, no, actually, if that is the definition of a projection matrix, then obviously projections and indifference are the same, but,
I've just never got the difference. I don't get it.
yeah, there might not be a
I
difference.
don't know.
Actually.
I've always kind of like wondered what the indifference, like, it seems, what's that word?
Yeah, I'll find out for you.
Do you
and
want
I'll
us to
let you
just
know.
email you pictures?
Yes, sorry, I'll